Hi, stats students. Today we're going to go through one sample t-test for mu, okay? Let's get started. A one sample t-test for mu is similar. The process is similar to a z-test. The difference is a z is for proportions, where a t is for means, okay? Proportions are categorical variables. Means are quantitative variables. Okay. Diced tomatoes are manufactured using 15-ounce cans. The quality control manager is concerned that the cans do not contain 15 ounces. He would be concerned if the cans averaged more than 15 ounces, because this would mean that the company is losing money. He would also be concerned if the cans averaged less than 15 ounces, because the consumer organizations will release negative publicity about the company. The manager randomly selects 49 cans and finds the sample mean volume to be 14.9 ounces with a standard deviation of 0.3 ounces. Is there sufficient evidence to believe that the cans do not contain an average of 15 ounces? Okay, so what we're going to do here, guys, is we are going to do the state plan do conclude. And in the state, we need our parameter. That's our mu. That's what's describing the population. We need our null hypothesis, which is the value that is describing the population. And then we need our alternative hypothesis. And that's what we're trying to find evidence for. Now, this evidence isn't always necessarily a good thing, but it's evidence that allows us then to make a decision, okay? And then finally, alpha. And alpha is that level that helps us decide, do we reject or fail to reject the null hypothesis based off the p-value compared to alpha. Let's get started with mu. Mu in this case is going to be the true mean, what's describing everything. So in this case, if you don't know, look at the question and see, what can that help us? Is there sufficient evidence to believe that the cans do not contain an average of 15 ounces? What is that average? That average is of the diced tomatoes, okay? So I put for mine, mu is equal to the true mean amount of tomatoes, it should say diced, tomatoes in a can, okay? Next is our null. So that's saying, what is the value of this right now that is describing the population, the current truth or the current claim? And that is that 15 ounces right there. So we say mu is equal to 15. And then we're saying, what are we trying to prove? And that's where we go to the actual question. And that question will tell us, is it going to be a less than, a greater than, or a not equal to? Okay. So in this case, it says, is there sufficient evidence to believe that the cans do not contain an average of 15 ounces? That means it's not a less than, it's not a greater than, it's a not equal to. So let's draw a line through that equal to right now. Okay, next, right? Next we have the plan. Oh dear, let's see here. Give me 1 second, I need to pause. I have a new computer because mine is broken right now. Okay, sorry guys. Like I said, my computer broke, so I'm working on my daughter's computer now. Okay, so now we have the plan. So that plan is the same thing that we did last week with RIN, okay? R is our random sample. I means independence. 10 times our sample size has to be less than our population size. And finally, N, our sample size, has to be greater than or equal to 30. With the method of a one sample t-test for mu. Okay, first one, R. In here, does it say we have a random sample? And it does. We have a random sample of 49 cans. So that's right there. R is equal to a random sample of N equals 49 cans. Now keep in mind, I'm not teaching at the board right now, so I'm not walking around waiting for you to write it down. So you're going to have to pause along the way to write this stuff down. Okay, next, I. We're going to take this sample size and multiply it by 10. And we don't know the population of all cans. So we just write down all the cans. 10 times 49, we assume, is less than all of our cans. And then finally, our sample size has to be greater than or equal to 30, and it is greater than or equal to 30. So we're okay to proceed with our method of a one sample t-test for mu. Now, a common question is, do I always have to write down the method? It's a weird year, you guys. 2020. I'm not there monitoring it, but you do need to know when you guys get to college and you take statistics, that is part of it. Like that plan going through those conditions are saying, hey, we met our conditions and now we can use this test. And that's what we're stating. Similar to, let's say you had a bad knee or you tore your ACL or something happened. You go to the doctor looks at you and says, yep, the knee is actually messed up. Here's what we're going to do. We're going to go in and we're going to perform a procedure to fix your knee. Okay, so that's kind of what this is going through. Here's everything that we need, and now we can use this procedure. Okay, do, state, plan, and now we're at the do, okay? And the do is similar steps to that z-test that I taught you guys a couple weeks ago. So step 1, we're gonna look for that X bar, and you can write that out like that, okay? Mu, you can also, and now rewind, X bar is your statistic. It's describing your sample. Mu, you've already written down what that is. That's from the null hypothesis. And the symbol for mu, again, it looks like that. And I'm using my mouse. Give me a second. I'm going to actually get it. Okay. So it's a little messy. The standard deviation is the same one from last week with the interval, excuse me. So I'm going to take that sample standard deviation they give me, Sx, and I'm going to divide it by the square root of n. And instead of SD, I like to say sigma. It looks like that, okay? That is your standard deviation of that sampling distribution. Okay, so we take that standard deviation they give us and we divide it by the square root of n. And then we have a t-score instead of a z-score. What is a z-score? A z-score is our ZOM's observation minus the mean divided by the standard deviation, okay? So the same thing, TOMS, it's what we observe. We observe what's happening to the sample, X bar. So our t-score is equal to X bar minus the mu, okay, the mean of the distribution, divided by the standard deviation of the distribution. And I'm going to use that sigma there. And we use that t-score with degrees of freedom of n minus 1. Okay, let's go through these steps then. First one is X bar, and that's saying what in here is describing the sample 49, and that is 14.9. Okay, so I'm going to go down and I'm going to write X bar is 14.9. Number 2, okay, that's our mu. We've already said what that value is, and that value is in that null hypothesis right there, 15. Number 3, the standard deviation. So they give us the standard deviation for the sample, and that standard deviation for the sample is 0.3. And now we have to divide that by the square root of the sample size, so the square root of 49. And I did that right there, and I got 0.04. Step 4, I'm going to find that t-score. And again, why I like this, you guys, is and that looks like it's an 8. It should be a 9. You guys forgive me. So it's 14.9, step 1, minus step 2, 15. Hit enter in your calculator. Divide by step 3 to get negative 2.5 with a degrees of freedom of 48. Okay, now we're going to practice what we learned yesterday to find that p-value. I do need to pull it up right now because I don't have it. Give me a second. AP Stats, formula sheets. Here we go. And here we go. We're at table B, okay? So I have my degrees of freedom over here on the side. And if I go back to what I have, my degrees of freedom are 48, okay? So give me a second. If you notice, 48 is not there. So what we have to do is we have to round down to the nearest one on the table. So even though 48 is closer to 50, we're conservative in our estimates, so we round down to 40. So this is the line we're going to be working with, okay? Okay, so just what we learned yesterday. Our z-score, sorry, that's not working. Our t-score is negative 2.5. Since it's negative, we take the absolute value of it, okay? So that's 2.5. And I look and I say, what space does that belong to? It's got to be between the left column and the right column. It's got to fit right in the middle. So 2.5 obviously doesn't fit right there. So I keep scrolling across to see where does 2.5 go. And 2.5 is right in between 2.423 and 2.704. Okay, so I fit right into that space. Now what do? I scroll up and I see that my p-value is between 0.005 and 0.01. Okay, so p-value is in between 0.005 is less than my p-value. I'm just going to put p, which is less than 0.01. Now here's the catch. If it was a less than or a greater than, we'd be done. But since our alternative hypothesis is a not equal to, okay, since it's a not equal to, we have to multiply these two values by 2. So times by 2 to get 0.01, times by 2 to get 0.02. Okay. So again, let's see here. 2.5 was my p-value. Let's just double check. We have that all right. Okay. We went to 40 just to review with you real quick. I just want to double check my work. 2.5 is right in between here. Okay. I scroll up. I got 0.005 and 0.01. And I have that right there. I multiplied by 2. And here is my final p-value. Okay, that's it for you guys. We just did the state, plan, and do. Okay, you'll have a work day tomorrow over this, then one more video for the week. It's your last video of new learning. Okay, you guys are doing amazing. Keep it up. Take care. Stay safe. Stay healthy.